Okay, hello everyone, welcome back. Before we start, I just wanted to make two quick announcements. I know you guys are busy this week with midterms and everything, but here's even more ways to get involved. So as you may have seen, the TA help hours of last weekend, they have been rescheduled to today, actually to this afternoon. So there will be additional TA help hours this afternoon. We'll have our regular TA help hours tomorrow as well, as usual. So we've sort of, reformatted essentially the format of of those TA help hours a little bit, in the sense that what we'll do is, in view of the midterm, right, that will be happening in a couple of weeks from now, we'll try to provide a little bit of a review for you guys in these TA help hours this afternoon and also tomorrow afternoon. So the TAs will be there, and we'll review quiz 1 and quiz 2 with you guys. So you may have seen I've posted detailed solutions to all the problems on quiz 1 and 2. And for each question, I also pointed out similar problems and questions in the textbook and the study guide and so on and so forth. So the TAs will be there, and we'll discuss with you the quizzes and similar problems. And so that should be a great preparation for the upcoming midterm. Also, each of these sessions will will also go over one random problem that may be relevant for next week's quiz on acoustics. So that might be an additional incentive to get engaged and participate in some of these TA help hours. So hopefully those will be very useful to you. I really encourage everyone to make use of them if you can. The other thing I wanted to point out is that for those of you, because I've received a couple of questions, so for those of you who think they need a little refresher on some, on some basic math related to trigonometric functions, to logarithms, basic algebra, these kind of things, I wanted to point out that we have on our physics department website a list of various tutorials that go through some of the foundations of trigonometric functions, basic graphing, logarithms, algebra. There's even a section also on unit conversions and significant digits, something that we covered explicitly in the course. So if any one of you wants to take a brief refresher on these kind of things, I think that's a great resource available to you. Okay, and with that, let's start talking about physics. So today we'll start a new module, a new topic, as I promised last time, which is geometric optics. Okay, so we'll first talk a little bit about what geometric optics is about, and we'll talk about some fundamental concepts like reflection and refraction. So the basic starting point really is the insight, right, that light can be described in different ways. Light, as I mentioned over the last 1 or 2 weeks, can be understood as an electromagnetic wave, which has very similar properties, mathematically speaking, to all sorts of ways that we discussed during the last lectures, during the last couple of weeks. They are very, similar mathematically to mechanical waves or acoustic waves, these kind of things. So in principle, one can represent light as a harmonic wave in many cases, in terms of its electric field E, written as some amplitude times sine of omega t minus kx plus some phase constant phi, right? And so this is the basic form of a harmonic wave. The same holds true for the magnetic field. And you'll actually discuss more about the wave nature light later in this course with James, but also especially next semester when you'll cover electricity and magnetism in detail. So light, sort of at a more fundamental level, is an electromagnetic wave. But it turns out that, for many phenomena, for many optical phenomena, especially those that are, that we're exposed to in our daily lives, most of them don't need that complicated description of electromagnetic waves to be applied, to understand those phenomena. For example, if you think of, just basic imaging of or reflections of images of a skyline, in this case here in complicated mirrors, or in other optical apparatuses like lenses or other things. In these contexts, it would be horribly complicated to describe light as a wave and try to look at all the different waves coming from different directions and how they superpose and how they actually give rise to an image. That would be overly complicated. And so what is a much more useful and practical approach in these cases is what we call geometric optics. It is a macroscopic description of light and is really the key to understand many phenomena that we're exposed to in our daily lives. So in sort of more concrete terms, what we mean by geometric optics is that essentially all we assign light is a direction of propagation, and we call that a light ray. So we assign a light ray to the propagation direction of light. We endow this light ray essentially with some wave type properties, like a wavelength. For example, we'll talk about light or light rays of a certain wavelength or frequency, right? We'll usually endow it with a propagation speed c. So the light speed, which will depend on the medium, it's different in vacuum than like in other media, like water or any other liquids or any solids. We also usually endow it with some intensity I, which is usually typically, similar to the intensity we define for harmonic waves in the last couple of lectures. And also sometimes we talk about polarization of light rays, although that's a topic that we won't really touch upon in this course. There's a question? Yeah, exactly. So light can interfere. So because at the more fundamental level, it is a wave, as I said. You're absolutely right. It gives rise to exactly the same phenomena like for other types of waves that we already discussed. So in particular, there's complicated interference patterns between different light waves, and they can be nicely observed in the lab. This is actually something we'll discuss more in the course. So you'll be actually discuss more with James later on in this course. So there are situations where it is essential to describe light in its wave nature because it cannot be understood with geometric optics. But those phenomena are sort of more on the microscopic scale. And I'll actually touch upon this just on the next slide, what the typical length scales or the typical situations would be for this geometric optics approach essentially to break down and sort of at the breakdown point where you would really have to resort to a wave description in order to understand phenomena. And that's essentially the last point here on the slide, right? So this geometric optics approach, or ray optics, as it's also often called, is really only applicable to macroscopic scales. So those scales that we can actually kind of see and experience in our daily lives. But sort of where is this threshold, right? And how can we actually create light rays or a bundle of light rays, a light beam in practical terms? So one way to think about this is the following, right? So consider this experiment here. So let's say you have a a harmonic wave of light. It doesn't matter how we generate it or where it comes from. Let's just imagine we have a perfect harmonic wave of light. Okay, that's somehow been created. And we can actually isolate a tiny patch of this plane wave, of this harmonic wave, and form something like a light bundle. So essentially an ensemble, like just a group of individual light rays, and can actually sort of experimentally realize really this kind of ray type optics in the following sense. So for example, consider we'll just apply these apertures to the incoming wave. So assume that this is, there's an incoming wave that's that fills all of this volume over here, and it hits this wall. And so this wall just selects this tiny bit, this bundle of light rays. And so what will happen is that this wave will just propagate through this hole of diameter d, and it will propagate in this direction. It will have these wave fronts, right? So these will be the periodic wave crests of that wave. That wave will have a wavelength lambda associated with it. And if you use the second wall, you can even like focus it better and make sure that all these wavefronts will be essentially perfectly parallel in the interior of that bundle of light as it passes through the second wall, right? And then so over here we should have this sort of perfect parallel wavefront bundle of light, and so it is kind of intuitively clear that, right, if we sit at this edge and look at this light bundle at the edge here, then we might expect some wave-like phenomena, some interference patterns, some diffraction happening at this interface between vacuum and this light bundle, because here the intensity really drops sharply from some sort of maximum intensity to essentially zero intensity over there. However, if we sit inside this light bundle, right, if this light bundle is wide enough, then these wave fronts in the interior will be perfectly parallel. And so we can just assign a propagation direction of that wave, which we indicate by these light rays. Okay, so that is essentially the conceptual idea of light rays. Light rays indicate essentially the propagation direction of parallel wavefronts. And so in the interior, these wavefronts will be perfectly parallel if this light bundle is wide enough. So what does wide enough actually mean? So in practice, it is observed that if this diameter d is roughly, an order of magnitude or factor of 20 or so larger than the wavelength of the wave, for practical purposes, the interior of that bundle of light rays of that wave can be essentially described as a bundle of light rays. And so the wave nature is not really important to understand the propagation of that light. So you will have somewhat parallel wavefronts in the interior. So this is essentially giving you a limit for when ray optics would be appropriate, or vice versa would be expected to break down. We would close this hole and make it arbitrarily small. Essentially, this bundle of light rays will approach just a point source, and this point source will then just emit sort of radial waves, so spherical waves, as we discussed with acoustics last week. And so then we would not be able to, then we would not have these perfectly parallel wavefronts. And so we would not be able to understand the propagation of that light in terms of light rays. It would be more of a light of a wave phenomenon. And so this, just this rule of thumb, written down explicitly, if you take, say, 500 nanometers of light, so that would be kind of greenish light. So this is where our eyes are essentially most sensitive at roughly 500 nanometers. This means that the diameter of such a bundle needs to be of the order of 10 micrometer for it to be considered as a macroscopic bundle of light rays or a light beam. as we call it. And there's a question. Yeah. Yeah, exactly. Exactly. And so conversely, it means that if you want to look at optical phenomena, so at imaging essentially of objects by light, and for it and for this, whatever experiment, so for geometric optics to be applicable to that experiment, that also means that the size of these objects must be larger than this limit of d, which means 20 times, roughly 20 times the wavelength of light. As soon as that is the case, if, for example, you put an object like this vase in, say, a parallel, you just apply such a parallel a plane wave to that object, then instead of complicated interference patterns behind that object due to the wave nature, you will just see this radial propagation of light rays. There will be some, diffraction and wave type phenomena at these edges, but they are sort of completely negligible on macroscopic scales. And instead, on these macroscopic scales, what you will see is the formation of a shadow, okay, which you can easily explain just by taking this ray nature of light that indicates the propagation of light, and you just draw these lines, and you can see that there's no light that can be sort of diffracted into the shadow here, and so you will create a shadow that separates these illuminated areas, and so that is a phenomenon that can then be easily understood just with ray optics, and you don't need to consider the wave nature of light. Okay. Any other questions on this so far? Okay, so then let's move on and just illustrate this sort of ray optics concept a little more, because it's really super important in many areas, and you certainly know of many phenomena where this plays an important role. So again, one very basic example, just to expand on this previous idea, is if you have an extended light source close to an object, or some light source that is actually bigger than an object, just by drawing essentially light rays from all the different points of the light source and toward the object, you can figure out that essentially, this situation here should lead to the formation of different types of shadows. So there's a full shadow, or umbra, as it's called, where essentially none of the light rays will ever be able to reach. While then there's also these partial shadows where only part of the light source will, only light rays from part of the light source will be able to reach the screen. So that's the partial shadow, or penumbra. And then there's these fully illuminated areas where essentially all points of that light source will be able to reach through rays, right? So these phenomena, these shadows that you can just see, and that's an incredibly simple experiment, right? Those can be simply explained with ray optics. You would just start drawing light rays emanating from the light source, and you will figure out that there has to be some sort of shadow, and partial shadow and full shadow. There's a question? Yeah, exactly. So they will depend on the distance between the object and the light source, as well as the screen, and also on the size of the light source. So one other famous example is our solar system, right? And so geometric optics is very powerful in that sense. It can explain some basic astronomical phenomena like lunar eclipses, for example, right? So just by using the fact that the sun is an extended light source and the Earth is an opaque object, you're in the same situation essentially as up here with the this light bulb and a vase, right? Here just replaced by gigantic astronomical objects like the sun and the Earth. And you can easily figure out by just using this ray optic approach and forgetting about diffraction of light in a wave type nature, that there must be a umbra, a full shadow, and partial shadows, the penumbra. And if it just so happens that the moon enters this umbra, right, we'll have a lunar eclipse. So it's a very simple but yet powerful concept that can explain lots of things. Another very interesting and I think really remarkable and impressive example is from actually 2,000 years ago. And this is, this is at least as old as geometric optics is. It was used by a Greek astronomer and mathematician to actually figure out what the radius of the Earth is. Okay, and I think that is very surprising. So he figured out that at a particular day during the year, light would be, so these light rays coming from the sun would be essentially perpendicular to the surface and would directly go into this well in a place in Egypt and in Syene. And he also noticed that at the same time during the year, in Alexandria, in Egypt, some distance away, there would be actually a shadow. So if there was a big, column, and that shadow, and so the same light coming in from the sun would produce a shadow there. So it would not be perpendicular to the Earth's surface. And so then by just measuring essentially the angle of that shadow, he was able to figure out what this angle between the two directions of these cities are, okay? And he just rudimentarily measured then the distance between these two cities. And that was a really rough guess back in the day, right? That's more than 2,000 years ago. But the impressive result is that he found, just by this crude, essentially extrapolation, this crude estimation, he found a radius, a value for the radius of the Earth that is actually 10% accurate. And I personally find that really astonishing and fascinating. So that was, ray optics in use more than 2,000 years ago. Yeah. Say again? Yeah, no, so they were not, so as far as I know, they were not known back then. But it was known, so you don't need a sine or cosine here to figure out what that is, because you just need to realize that that's part of a circle, right? And so this length over the radius equals the angle, right? So you actually don't need trigonometric functions here to figure it out. You just need to take the ratio of that piece of the circle over the radius, and that equals the angle. Okay. All right. So those are some I think very interesting examples. So let's dive into geometric optics a little bit more. And so before we talk about reflection and refraction, I wanted to introduce a pretty important concept, which is the concept of images. So whenever we do optics, right, the goal is always to have some object, some optical apparatus that produces some image of the object. Okay, so optics is really about imaging, about generating images of an object with some type of optical apparatus. And so there's two qualitatively different types of images, which we call real and virtual images. And as the name suggests, real images are real and virtual images are virtual. They can actually not be observed on the screen. So real images is something that you can actually see. If you put a screen there, as an observer, you will actually see an image on that screen. While for virtual images, it is just a construct that our brain comes up with. But that construct that our brain creates cannot be visualized on a screen. So it is not a real image. of an object. And so two basic examples are here. So for example, one of the easiest optical apparatuses you can think of is just a basic lens. Okay, so let's say we have some object here, A, and let's consider some light rays emanating from one of the points of that object A. And so as they hit the lens, as we'll discuss more on Friday, these light rays will be bent. And in this case, for such a lens, will actually converge at some point. And this point of convergence is what we call the image of A, okay, of that point A. And whenever we have an optical apparatus where these light rays emanating from a point will eventually converge onto a point, that is what we call a real image, okay? Because if I would place a screen here in this plane at A prime, and my laser pointer is getting weak. So if I would put a screen here, you could actually see an image. So you would actually see the image of A. It would be inverted and it would be a little smaller than the original, but you would see an image there. So that's what we call a real image. Same thing happens, for example, in a pinhole camera. You may have seen this before. It's essentially just a box with a tiny hole in front. And that was actually the original concept for the first concept used to do photographs, okay? So that is really the basic idea of the first photographs that were made in the 19th century. And the idea here is that you just put this tiny hole in front of a box. You have a screen in the back, which is where the photo would be created. And this pinhole camera here allows you to just image an object, for example, this guy here, onto the screen in a one-to-one fashion. So since this hole is tiny, from each point of the object, there's only one light ray that will go through this pinhole and eventually hit the screen at the back of the pinhole camera. Okay, so we will have a one-to-one mapping between each point of the object and the screen. And so that's one of the most simple optical apparatuses. And as I said, it was the foundation essentially of photography in the 19th century. On the other hand, the easiest example for a virtual or imaginary image is a mirror, right? And we are all familiar with that. So if you see an object A in the mirror, so let's again say we have this object here, and we see light rays emanating from a point on this object A, they hit the mirror and eventually hit the eye of an observer. Now, our eye doesn't know about reflection, so it will just follow these light rays back in the other direction, and will construct a virtual convergence point of these rays. And so this is a virtual image because the convergence of these light rays is just a virtual construct that happens in our brain. And so this is a virtual image. If you put a screen behind the mirror, you will not see an image on that screen. Okay, it cannot be captured, visualized. It's just a concept. It's just a construct that our brains comes up with. The more complicated scenarios, and we'll discuss this again more on Friday, is if you take a different type of lens. So this is what we call a biconvex lens, and this is a biconcave lens, so two concave surfaces. So if you look at light rays emanating again from an object A that hit this lens, the lens will actually make those light rays even more diverge. So if you had an observer over here looking toward the lens, again, our brain or the brain of the observer would not notice that they have been deflected, but instead will follow them to the other side and create a virtual convergence point. And so it will create this imaginary image here, A prime, of the point A, which is upright. It has, so in contrast to this lens here, it will be upright and it will be smaller, but it will be an imaginary image that again only exists in the in sort of the brain of the observer. Okay, so it's important to realize that there's these two different types of images, and we'll talk more about this on Friday. All right, so now let's talk about reflection. So that's one fundamental concept in geometric optics, and is sort of the basis for all for mirrors, and also in some sense for lenses, and we'll talk about lenses on Friday. So the starting point here really is essentially one of the fundamental essentially axioms or hypotheses on which all ray optics and geometric optics is essentially built upon, which is called Fermat's principle. And so Fermat essentially hypothesized a few centuries ago that if you have two random points in space, that the path that light chooses to get from A to B, or from point P1 to P2, would be the path with the smallest travel time. Okay, so light would always choose a path in which it minimizes the travel time between the 2 points. So that is known as Fermat's principle, right? I mean, intuitively, it's clear to get from one point to the other point. There's an infinite amount of ways, of paths, of how I can connect this point P1 to P2. But light would choose the one with the minimum travel time. And if it's a optically homogeneous medium, so if the propagation speed is constant, it's the same everywhere, then, I mean, everyone would guess, right? The shortest travel time should be reached when light travels on a straight line between the 2 points, right? That would be the shortest distance, and if the speed is constant, right, it should correspond to the shortest travel time between the 2 points. And so this is, and from this principle, it automatically follows that light should travel on straight lines, meaning light should be represented by light rays, and that is kind of sort of the conceptual basis for geometrical optics. Okay, question? Can you speak up a little bit? I only understood propagation speed of light. It is. Yeah, it is. So the speed of light is different in vacuum from air. It is different in water. It is different in some solids like glass, and these kind of things. And this is why, and this is exactly why refraction happens. And we'll talk about this in a couple of minutes. So the fact that the speed of propagation changes from medium to medium actually gives rise to very interesting optical phenomena. And we'll talk about this in just a couple of slides from now. Yeah. So in other words, right? So if the speed of light changes in between P1 and P2, then the shortest travel time may not be the straight line going from P1 to P2. And this is exactly what gives rise to refraction. And we'll talk about this in just a few minutes. But let's first try and understand what actually happens when light rays reflect off a surface. Okay, and we'll use the same concept then and apply it to refraction at between two different optical media with different propagation speeds of light. So let's think about the following scenario. So it looks a little crowded here, but let's go through this sort of step by step. So let's again choose 2 points. Okay, we just randomly choose them, P1 and P2, in this plane. And let's assume they have coordinates x1, y1, and x2, y2. And let's assume that we're actually interested in reflected rays. Okay, so we're not interested in direct propagation from P1 to P2, but instead we want to reflect light rays off of a surface down here, which we place, for convenience at y equals 0. Just to make our life simple. And so I guess everyone would agree, right, that there's again an infinite amount of ways of how to connect P1 and P2 by going via the surface, via this reflection surface, right? So for example, you could choose this green path here. You could also reflect right over here and then go back up here, or you you go this way here and then reflect back up here. So there's an infinite amount, infinite number of ways of how to do this, right? So now let's apply Fermat's principle and find the way that light actually takes, namely the one that minimizes the travel time. Okay. It's also clear that if this medium is homogeneous, and we'll assume this, right, then it has to be a straight line, as we concluded up here. So it cannot be some arbitrary curve. So it has to be so the path has to be the sum of two segments, of two line segments. So in general, we can write the travel time as the length of one line element plus another line element over the propagation speed c, right? That would be the total time that light takes to go down to the surface and up again via any path, okay? And we'll let S1 and S2 be two arbitrary line segments, okay? And so this reflection point, so we'll keep this reflection point flexible. So we'll just denote this as r of xr comma 0, where 0 is just the y coordinate. So it just expresses the fact that it's on the surface, on this reflecting surface. And so the length of S1, right, is simply the square root of this side squared plus this side squared, right? So if you look at this triangle here, the rectangular triangle, so the length of this side is just square root of this side squared plus this side squared. So this would be xr minus x1. So xr minus x1, this part here squared, and then plus y1 squared, which is this side. And then the same for S2, right? We have x2 minus xr squared. So this side plus y2 squared, this side. So this would be our general expression for the travel time that light takes, okay? And now we apply Fermat's principle, right? We say we require this time to be minimal. So here xr is a free variable. All the other numbers, all the other quantities are given, right? We fixed these 2 points, P1 and P2, with x1, y1, and x2, y2. The only thing that we're allowed to vary is this reflection point. And we'll use Fermat's principle to fix that reflection point and determine which path light actually will take, okay? So we'll take the derivative of that time t with respect to xr and require that to be 0, which is a necessary condition for a minimum of that function, right? So the derivative has to vanish. Now we can compute the derivative. The derivative of a square root is 1 over 2 times the square root. There's an internal derivative xr minus x1. Same thing for the other term. It picks up a minus sign because of the internal derivative here, which allows us to bring this to the other side. So we have essentially this expression here. And you realize, right, you notice, so down here is again the length of the segment S1, and this square root here is S2. So we can just write this as xr minus x1 over S1, x2 minus xr over S2. Now, if you just look at the geometry of this, right? So xr minus x1 is this side here, or this part up here, over S1 over this side, right? And this is just sine of alpha 1, right? So we can relate this fraction to the angle alpha 1, and the same thing for the other side. So x2 minus xr is this side over S2 is this side. So this is sine of alpha 2. That's just the definition of the sine function, right? In a rectangular in a rectangle. Okay. So we conclude that sine alpha 1 equals sine alpha 2, or in other words, alpha 1 has to equal alpha 2. Okay. So Fermat's principle tells us that light reflects off a surface in such a way that the angle of incidence with respect to the normal of the surface equals the angle of reflection. With respect to the normal. So alpha 1 equals alpha 2. That is the path that light will choose as it's reflected of a surface. And that's known as the law of reflection, right? So formally, the angle of incidence and reflection with respect to the normal of the reflecting surface are equal. Okay, and it directly follows from this from Fermat's principle. Any questions on this? Yep, I don't know who was first. Yeah, you go. Say again. XR and R, yeah, right. So R is the point of reflection, okay? And so that point of reflection can be anywhere on this surface, right? And so we would like to find out where this point of reflection actually lies, okay? Because as I said, right, I mean, the light ray could take all sorts of different paths. It could take this green path here, and then the point of reflection would be over here. The light could reflect off, over here, and then shoot back up here, and same thing on the other side. So we don't know where this reflection point really is, and so we want to find out with Fermat's principle where it's located. So we want to find out what this XR, so the horizontal location of that point actually is. And so minimizing the length of these two segments, right? So we can, for any possible path, we can add the length of these two segments, and then compute what the travel time is, namely just the total length over the speed. So S1 plus S2 over the speed, right? And so this function here just tells us for any location XR, so for any location of a reflecting point along the surface, what the travel time would be for light that chooses to go through that reflection point, okay? And so we want to minimize that function, and that determines XR, so the location of R. And what we find is that this location XR is located such that these angles are equal, okay? It's a little complicated, it's a little convoluted, but essentially what we find in the end is that these angles have to be equal. Make sense? Okay, yeah. Excellent question. So that's in 2 slides from now, okay? If they reflect into a different medium, then the light ray will actually be bent toward or away from the normal, depending on how the propagation speed changes. We'll discuss this in just a second. I just wanted to, as a brief application of this concept, let's consider this very practical situation, right? You're watching yourself in a mirror, right? And so let's say you're 180 tall, 180 centimeters tall, and so the question is, you want to buy a new mirror, right? And the question is, how large does it need to be for you to be able to see yourself in full length from top to bottom, okay? So you're 180 centimeter tall. How big of a mirror do you need to purchase, to buy, for you to actually see you, in full length explained in a virtual image behind that mirror? Yeah, you were very fast, but maybe we'll ask you. Say again? 60? That is not exactly right. Okay. Yeah, kind of. So it turns out it is actually not dependent on the distance that that you're away from the mirror. Okay. Okay. Excellent. Yeah. Right. So the correct answer is it has to be 90 centimeters. Okay. And it has to be hung in a certain way that you can see yourself, right? In full length. So the question now is, why does it need to be 90 centimeters? Yeah. Exactly. And there's actually two steps to this idea. And there's actually a nice cartoon in the textbook. So I borrowed this cartoon from the textbook because I actually like it. So let's say you're watching yourself in a mirror here on this wall, right? Then, as you correctly said, right, since the angle of incidence equals the angle of reflection, to see, your toes essentially, or your shoes, the mirror has to at least cover half the distance between your eye and your foot. Okay, so it has to cover this part, but then also to see the top of your head, again, you need to cover half of the distance between the top of your head and your eyes. Okay, so it's half of both lengths, which means half of your total length. If you're 180 tall, so it's 90 centimeters. Okay, so it's a pretty simple, straightforward application of essentially Fermat's principle. Okay, so that is pretty interesting. So in the last 2 to 3 minutes, let's consider exactly the question that you raised, namely what happens if light travels from one medium to the other medium, and how does it propagate? So the same thing here. We apply the same concept. We apply Fermat's principle and ask for the shortest possible travel time between 2 points in different optical media. So let's pick point P1 up here and say this is some optical medium that has some propagation speed C1. And let's assume here's a surface that separates these two media, and you have a different medium down here which has a different propagation speed C2 for light. And we'll pick just a random point here in P2. And so the question is, what is actually the path that light takes between these 2 points? Meaning, what is actually the path that minimizes, again, the travel time between the 2 points? So we simply play the same game as before, right? And we'll essentially cut this into 2 parts, S1, so one line segment between P1 and the surface, and then another line segment S2 between the surface and point P2. Again, the travel time will be S1 over the speed, over the propagation speed, plus S2 over the propagation speed. So here we have different terms because the propagation speeds are different, right? So before we were just in one medium, and so both segments had essentially corresponded to the same propagation speed. So here we have 2 terms. Again, just looking at these triangles here, we get again the square root of xr minus x1 plus y1 squared as before. And here as well, just we have a different prefactor now because of the different speeds. And if we again take the derivative of this with respect to xr to the reflection point, we find that in this case, sine alpha 1 equals sine alpha 2, but divided, so each term divided by its respective propagation speed C1. So that was the same factor before that just factored out of the equation. But here it appears explicitly because simply the speeds differ in the 2 media. And so this is the law of reflection known as Snellius or Snell's law, which says that n1 times sine alpha 1 equals n2 times sine alpha 2. And so n here is the quotient of the propagation speed of vacuum and the actual propagation speed of the medium. So n essentially measures how much the speed differs, the propagation speed of light differs from that in vacuum. And that is what we call the index of refraction, okay? And so the interesting thing here is also that we did not make any assumptions about which direction light travels, right? If it travels from P1 to P2 or vice versa. And so that's an important fact because it tells us that the path of light is reversible, right? Meaning that if I can see you, you can see me, okay? Even if light propagates from one medium to another medium, or goes through a complicated apparatus where it's being refracted and multiple times or so. So that's an important principle that the optical path is always reversible And that is really because Fermat's principle only asks for the shortest propagation time. It doesn't say anything about the direction that light travels. So it's very important to realize that that in geometric optics, the optical path of light is always reversible. And so if you just look at this law, and I'm sorry to go one minute over time, there's 3 important cases. So obviously, if the ray is incident with a 0-degree angle toward the normal, then it will just go into the medium without being deflected. So if alpha 1 is 0, then also alpha 2 is 0. If the light propagates from a thinner medium into a denser medium, meaning that N2 is larger than N1, then the light is bent toward the normal. So in this fashion, so alpha 2 is smaller than alpha 1. If it's the opposite case, if it goes from a thicker medium into a thinner medium, then it's actually bent away from the normal, like in this case here. You have a smaller angle here and a larger angle in this other medium. And then also, there's a critical angle. If you go from a thicker medium into a thinner medium, there's a critical angle at which light is not able to actually propagate into the other medium. So there's no solution essentially to Snell's law in this case. And above that critical angle, it is reflected back into the medium. It is not able to leave that medium, and that is what we call total internal reflection. Okay, and you can actually use Snell's law. You can solve it for this critical ratio of the 2 indices of refraction. And so for water, for example, between water and air, it's something on the order of 48 degrees or something. Okay. I think that's a good place to stop. We'll do a few exercises on this next time and discuss in more detail. See you on Friday.